here Kostya Aleshkin. He was PhD student in CIS a few years ago, 5.
Yeah.
Yes. And then now he's in mathematics department of Pavilion University, New York. And he told me right now he's going to move in summer to IBM for in Tokyo.
Right.
For another postdoc. So please.
Right. Yeah. Thank you very much for invitation, for introduction. It's really nice to be here after all these years. So right. So how many people identify the mathematician? Okay. Then I'll try to be gentle. So yeah. So let me say a couple of words about like what this talk is going to be about. So this is one of the big things I've been thinking about in the recent years. So probably people heard words GLSM, and maybe some people work with. I mean, I know that some people work with GLSM, but if you haven't worked with GLSM people, you probably heard about them. And what I want to explain is that how GLSM appear in mathematical context, and how we can compute some correlation functions in mathematical context, and then relate them to physical objects, sphere functions, hemisphere functions, solid torus functions, and then explain maybe some interesting examples that we have, some applications. But let me start in order. Right, so please ask questions, right? Because again, I might talk something trivial, I might talk something complicated, or something unknown. Anyway.
Do you expect that everybody knows what is a GLSM?
No. So, right. Basically, it's going to be, I plan to split the talk in 3 chapters, and probably there will be not enough time for the part 3, but let's see. So part 1 is GIT quotient, or symplectic quotient. Part 2 is going to be enumerative series. Or curve counting. Sorry. And part 3 is going to be the invariants. And they're generating series. Okay? So let's start with part 1. So this is, I think a lot of people are familiar with this, but it's good to, I guess, talk a little bit through it so that we're on the same page. So first of all, let's just think about a complex projective space of dimension n. So a complex projective space with dimension n is a complex manifold which we can think about as a set of n plus 1 tuples of complex numbers, x0 up to xn, up to a scaling by a common factor, which I call lambda. Right? Where x is not identically 0. So another way to represent the same complex projective space would be to think about it. Oh, sorry, right. So this is a quotient of complex space of dimension n plus 1 without the origin, modulo a rescalings by complex number, modulo C star. Another way to think about the same complex projective space would be a quotient by a compact Lie group, in this case just group of U1. So we can think about it as a unit sphere inside Cn plus 1. So surface given equation by sum of absolute values of xi squared equal to 1. Quotient by the action of U1, which just rotates all the arguments of xi's by the same number, right? And this is a trivial example, or maybe like one of the simplest examples of a GIT, or symplectic reduction. And let me just write a couple of words about it in algebraic setting and in symplectic setting. So more generally, we'll consider quotients of vector spaces by reductive groups, and this is, well, because this is a linear sigma model, so let V be an n-dimensional space, big n-dimensional, and let G be a complex reductive group. With linear action on Cn, so we can think about it as a subgroup of GLV. And for most applications for now and for today, you can just think about it as being subgroup of diagonal matrices in GLV, so some torus of a different dimension, which I'll call kappa. Okay? But again, in more general, this could be product of GLNs. And in this symplectic setting, we'll consider the maximal compact Lie group inside G. So in fact, you can think about reductive groups as, the groups that complexifications of compact Lie groups, right? And then there is going to be a Hamiltonian action of G on V with respect to symplectic form, just dxi wedge dxi bar, and a moment map mu. It's going to be a map from Cn to the dual of the Lie algebra of the group. And in this case, this is just going to be just C to the kappa. Oh, sorry. Let's do it real. Okay. And so in the algebraic setting, as for Pn, if we're considering a GAT quotient, we want to remove some points from the vector space, like here remove the origin, and then take the quotient of the remaining subset. So, but first we need to choose a stability parameter. So let zeta, in general, this is going to be a character of our group G, maybe a Q character, rational character. Well, then we can form a covariant line bundle over Cn. So let's say, so K is some natural number. Z is our character. Then if we choose the number to be the denominator of this character, then we can make sure that the action of group G on this C is honest. So the weight of the action is just given by this character. And then this is going to be a covariant topologically trivial line bundle over V. And then we say that a point X in V is zeta semistable if there exists a non-zero polynomial function which transforms under the same weight as K times zeta, so a section of this line bundle. So a section of this bundle such that this section does not vanish at this point. Okay? So what does it mean in the case of Pn, for example? In the case of Pn, we can take zeta. Well, so the group that we're taking quotient with respect to just C star. So characters of C star are just, well, powers of this number. So let's say zeta is 1. Okay? Then sections of Well, those are polynomial functions on V that have weight k times 1 with respect to C star. So those are homogeneous degree k polynomials. Are degree k homogeneous polynomials on V. Well, so a point is semi-stable if and only if there exists a homogeneous polynomial that doesn't vanish at this point. And for every point which is not identically 0, we can find such a polynomial. So the only point which is not semi-stable, a stable point, is just 0. Okay, and so in the algebraic setting, the GIT, so GIT stands for Geometric Invariant Theory. It wasn't introduced by Mumford, but GIT quotient stack, it's slightly different from just usual GIT quotient, but it doesn't really matter. So is defined as, so I'll call this big X sub zeta to stress that it depends on the stability condition, and later in the talk I'll drop zeta sometimes. And this is going to be, so analogously to the PN case, we'll just remove the unstable points. We just take only semi-stable points. So V zeta semi-stable. Set subset of points in V that are semi-stable. Quotient our group G. So the square brackets means that this is a stack quotient. In other words, remember stabilizers. In other words, if there are points where the group does not act freely, we remember that there is some residual gauge group. Okay? So now in the symplectic setting, oh, this one? Yes. Sure. Okay? So in the symplectic setting, we can also form the quotient, symplectic reduction. And then we also take at zeta. Now we can take it from, well, so in the case where G is a torus, which I'll now assume, we can just think about it as so element in the dual Lie group, Lie algebra. As a real valued character of G. And then we define the symplectic quotient, or symplectic reduction, again as a stack quotient of the pre-image of the moment map. So the moment map is your Hamiltonian, right? So for each like Lie algebra element, you have a vector field, and then you have a corresponding Hamiltonian. And then you're taking the pre-image of the moment map of this character you choose. And then again, you take the stack quotient with respect to your compact Lie subgroup. And in the case of Pn, so the moment map, this is just sum of absolute value of xi squared for the diagonal action of U1. And then if you take z equal to 1, then here is your moment map equation. So this is pre-image of the moment map at the value 1. And then you take the quotient with respect to the U1. And then there is a theorem, so a version of Kempner theorem, that tells that under mild assumptions, well, those are the same, right? As complex variety, complex many. So there are two ways to think about GIT quotient or symplectic reduction, or you can think about gauge linear sigma models. So now a GLSM is a two-dimensional n equal to 2, supersymmetric theory with, so what's the field content? So the field content is that we have n chiral superfields, well, each for a coordinate of our space V. And then we have a gauge field in the joint representation of our group G, right? And then if you don't have a superpotential, then you have the scalar potential. So scalar, I won't write the Lagrangian because it will be irrelevant, but you can imagine what it is. So the metric for the chirals is flat. This is just a metric on your vector space V. I'll only write the relevant part of the scalar potential. So this is going to be the moment map minus zeta, which was the stability parameter here in the GLSM setting is called Fayet-Lupul's parameter squared, maybe plus something about plus gauge part. Okay. And so if you want to consider the space of vacuum in your GLSM, well, this is going to be given by zeros of the scalar potential. So in particular, it will enforce the moment map equations. Fi, Fayet-Lupul's. I do not remember how to spell it correctly. Maybe someone can tell me? How do I spell Fayet-Lupul's?
Fayet-Lupul's.
Yeah.
With Y, E, T. I, E, O, B, O, no.
Great. Thank you. Okay. So, yeah, physically you can think about the symplectic reduction or GIT quotient as some version of space of aqua, representation of space of aqua for your GLSM. Right. So this GC action comes from the gauging the scalar fields, right? Okay. This was what I wanted to talk about GIT. Maybe let me make one more comment. Adding superpotential. Okay. So you can modify this construction a little bit by introducing an additional function, which is on the space V, which is going to be superpotential. So let's see. So introduce additional scaling action on V. So we call this. So this is related to the R charge action. Or I guess R symmetry action. So the weights of this star action on V are going to be proportional to the R charges. And, well, there are some conditions, but let's put them apart for now, for this theory to be well defined. But, and a superpotential. And this is going to be a polynomial or more generally holomorphic function. From our space of chiral fields or our vector space V to C, which is gauge invariant, so W is G invariant. and covariant with respect to the R charge action. So what does it mean if we have some lambda in the group of R symmetry? Then W of lambda applied to X, so where we apply it with respect to the R charges, is equal to lambda to some power times Wx. So in physical literature, this R is always 2. However, if this R is 2, then in general, this action will be only a fractional action. So if you want this to be an honest action, you have to actually to modify the R charges a little bit. So in general, R is going to be a natural number. Okay, and then the scalar potential in your GLSM will be modified as so the whole superpotential plus the square of dW plus some gauge part, gauge fields. So in other words, if you want to look at vacuum, now your space of vacuum is a critical locus of a function W inside your GIT quotient. So in this language, we're saying that we're studying the critical locus of some C star equivariant function inside this X. And same here. Okay, any questions about the setting? Great. So now I'm going to talk a little bit about the curve counting or enumerative theories in this setting. How many people know what Gromov-Witten theory is? Gromov-Witten? Okay, so around about half, maybe a little more. So let's see what I want to say about this. So in general, in this Gromov-Witten-type theories, in curve counting theories, what we do, so we consider moduli space of maps from some curve C. So this is a Riemann surface or algebraic curve. In general nodal. And also it can have orbital points, it can have finite stabilizers at the nodes or at the mark points. So there's going to be some mark points. Those are the points where we insert our observables, if you like. And then we map these spaces to some X. And X is usually a symplectic manifold or an algebraic projective right, if you like. And then you consider the space of all such maps, and this is going to be usually some finite dimensional, maybe singular manifold. And then you think about a space of vacuum in some supersymmetric field theory. And then when you want to consider some curve counting invariants, what you do is you have this finite dimensional manifold. If you are very lucky, it's smooth, it's compact. So you can just integrate some cohomology classes on this manifold. And this will compute you some observables in the corresponding physical theory. So usual life is not as simple as that, but so let's see. So here we're gonna work in the quasi-map setting. Quasi-map setting. by Konstantin, and Kim, and then Maulik. And then there are papers with superposition of several of those authors around the late 2000s, earlier 2010s. And so to describe what's a quasi-map, let me explain like one very simple example. So consider a very simple case. Maps from P1, complex projective space with dimension 1, which is like a sphere topologically, to Pn. So how do we describe such a map? Well, fortunately, P1 is just a set of two numbers up to two non-zero numbers up to rescaling, two simultaneously non-zero numbers up to rescaling. And Pn is just a set of n+1 numbers which are non-zero simultaneously up to rescaling. So if you want to describe such a map, let's say of degree d, you can think about it as a value of like classical action on such a map. Let's say natural number. As just a tuple of n+1 homogeneous degree d polynomials of x and y. So such a map is just P0 of small x and y. So this is homogeneous degree d up to Pn. Homogeneous of degree d. So each of these is just a polynomial. And, well, this is almost true, except, well, all of these polynomials have a common zero. You're in trouble because you are not landing at any point in the projective space. You are landing in the unstable locus, or in other words, you're landing outside of the moment map. You're landing not in the space of vacua. So what do you do? So if P0 up to Pn have no common roots, then, well, this tuple F defines a map to Pn up to rescaling. Because again, since the point in Pn, you can rescale the problem. So now, how do you think about this space of maps, right? So you can think about space of maps. Well, first of all, of course, if all these polynomials are identically zero, then it's a no-go, right? It's just like an identically mapped to unstable locus. So you remove this one. If you remove this one, you have n+1 homogeneous polynomial. Well, homogeneous polynomial of degree d is d+1 complex numbers. So you can think about it as a c to the d+1 times n+1 without the zero. Quotient C star, which is itself a complex projective space of dimension n+1, d+1, -1. Except when P0 up to Pn have a common root. By the way, this is called a loop space, and it was used by many people before the introduction of quasi-maps. So I think one of the first people who started this space are Morris and Plesser in the physics context, and the mathematics context there was Giventhal, and then there were a lot of people doing this. So Morris, right. Well, anyway, so it's called a loop space because, well, if you think about this, those are well-defined maps except maybe points at 0 and infinity of this P1. So those are actual maps of an actual loop of C star to P. So now, if you don't care about this common roots of Pn, so it actually gives you like a rational map from P1 to Pn. If you don't care about this, well, then it's a very nice space. It's a smooth complex manifold, compact, so you can integrate over there whatever you like. However, that's not what you have. And so there are different ways to resolve it. So Gromov-Witten theory way, a way of what's called stable maps, is compactify this locus, so where all the polynomials have common zero. It's a complicated locus given by like multiple equations. So compactify by adding nodal curves. So you can imagine if you have like a P1, you have some point on P1 where your map becomes bad, and then you just blow up at this point. So you develop like you rescale very much, like a lot, and then you'll just get another bubble on this P1. This is going to be a nodal curve, and this is how Gromov-Witten theory does it. But the quasi maps. So the idea that, well, if such loci are codimension greater than 0, you just ignore them. So ignore the fact that they do not define a map. And just consider this nice modular space. Okay? That's why they're called quasi-maps, because they're not actual maps. There are some points where these are, well, they're mapped on stable locus. And you just work with this modular space of maps. Again, this was a very simple example, but that's roughly what's going on. Now, how do you talk about this more generally, right? So this was Pn case. More generally, well, one way to think about such a map is first to choose a degree. So let me maybe it's like this. So what does it mean to choose a degree on Pn, right? It basically saying that we're choosing degree of the polynomials. And polynomials, homogeneous polynomials of a given degree are just sections of a line bundle of D on this P1. So this map, F, this is the same data as bundle of D over P1, or if you like a principal C star bundle, plus n plus 1 sections of this bundle. And those sections are exactly this P0 up to Pn. So in the general setting, a quasi-map well, you can think about it as a principal bundle over your curve, or your domain curve, which you can think about as a gauge bundle, because this is a bundle whose fiber is a gauge group, together with a section of the associated vector bundle. So if you have a G bundle, let's say you have a GLN bundle, you can always just act by, so you can think about transition functions for this bundle as matrices in GLN, and then you can just think about them as transition matrices of vector bundle, which is called associated vector bundle given to G. So this is a notation. And in the Pn case, this is just Cn bundle, so the sections of this bundle are just going to be n plus 1 polynomials of degree. Okay? So now finally we have to work a little harder to add the superpotential. So let's add W in the picture. So first of all, it's actually I haven't thought about it much, but like from the physical perspective. But it turns out that when you think about this 2D GLSM, so if you want to compute some invariants, you actually do a topological twist of the model, right? And then so when you think about the R symmetry, then you have so it comes from like gauging the it's not gauging, it comes from like a Poincare group on your image surface, and then you have like this odd charges, odd symmetries, which are spinors. When you do the topological twist, they just become like holomorphic forms, right? And so you can think about your R symmetry in this case as an additional U1 gauge symmetry with a fixed gauge bundle. So maybe this is wrong, but this is just something I thought that might be true. So mathematically, what you do, so first of all, you have your group GLV, right? Where both group G and C star R lives. And now you can just look at the big group that is generated both by gauge symmetries and by the R symmetry, which I call big gamma. And this is a group generated by G and C star R, as I said. Okay, so, and if you think about the quotient of this group, so G obviously, well, is a subgroup. And if you think about the quotient, well, this is going to be a C star because it's generated by these two groups, which must have just only finite intersection. But this C star actually is going to be, well, a quotient of this C star by maybe some, some root of unity. Mathematically, we can write such short exact sequence of groups. Well, and this map will give you a character of this big group gamma, because it's a group homomorphism from gamma to C star. And a mathematical model, the theory of GLSM and all the sphere functions only depend up to trivial factors. So they don't depend on the R charges, like per se. They don't depend on G. They only depend on the group generated by both R charges and gauge charges, and a choice of a character from this bigger group. Okay, so correlators depend only on gamma and chi. Well, in physical language, I guess you can twist your R charges by gauge charges without changing the physics much. All right, so finally, so this quasi maps with this R charge action, which are called in mathematics literature Landau-Ginzburg quasi maps. Well, you can think about them as, so let me write it like this. So you have a curve, like your image surface, your wall sheet. And then you have a map, so you want to map to V quotient, like the JT quotient of V mod G, but the quasi-map, it actually may land in the stable locus. So you can think about it as just a map to V mod G. But since, as I said, you want to treat G and C star R on almost the same footing, you actually map into V mod gamma. So this is your map. Now you can think about, okay, so let's just project this to point. So what's a map to such a stack? It is the same as a principal gamma bundle, with an equivariant map to V. The same data. So again, it's just a principal bundle and the sections of associated vector. So now you can just take this vector bundle. So B gamma, it's just mapped to a classifying stack of all gamma bundles. So this is just and now you can apply this character chi to the transition function. So your transition functions are functions in gamma. You can apply this character to this transition functions, and then you get just a line bundle. And this line bundle, so this is a condition that R symmetry is not actually a gauge symmetry. This line bundle has to be just the bundle of holomorphic differentials. Or if you like, spinors after topological twist. So this is just line bundle, a BC star, map to BC star. And this map has to be just a map of line bundle of holomorphic bundles. So we call this log canonical bundle on C. So I guess the details are not super important for here, so I won't stress on it. It takes some time to get used to this language, but are there any questions? Huh? So, well, BG is the classifying space of principal G bundles. So we have a topological construction, right? But basically, a map to classifying space is just a choice of a bundle. So this basically says, well, the arrow on top is a choice of a gamma bundle plus sections of associated V bundle, like a vector bundle. This says that, okay, we forget the sections, we just think about the principal bundle, like the gauge bundle. And this tells you that, well, now if you take a bundle, and then when you go by this character, you should go from your gauge bundle, like bigger gauge bundle, to just R charges, R symmetry bundle. And this R symmetry bundle is, as we know, like the bundle of holomorphic differentials. Makes some sense? A little bit? Okay. Great. So, okay. So I guess I won't talk about the details of the constructions and all the innovative geometry details here, but I want to say additional thing. So let LG, GN, X, zeta, W be the moduli space Actually, let's not put W here, because here there is no superpotential yet. The moduli space of this LG quasi-maps. Where G is the genus of C of the wall sheet, and this is number of marked points. So as usual in this type of theories, this space is very singular, it's non-compact, and then again it doesn't know anything about superpotential. So how do we work around all this? Well, we introduce a certain nice integration theory on it, or we introduce a virtual fundamental class. Right, so this formulation was done by Fan, Jarvis, and Ron about 8 years ago. And now there are many interesting ways how you can extract actual like maps to the critical locus that you're interested in, or maps to the vacuum space of your theory. Well, this is works by many people, so let me mention some. So Konstantin, Guerra, Favero, Kim, Shoemaker. And then, well, so first, okay, so one way was done by Fan, Jarvis, and Ron, but their theory does not quite produce all the necessary correlators. And then there is a paper that we use is by Favero and Kim, which basically defined all the correlators and show that the correlators define you like a nice topological theory. So in technical terms is called a cohomological field theory. But so introduce W dependent. So, well, this space doesn't have anything about W. Virtual fundamental class. So generalization of Behrend-Fantecchi virtual fundamental class. On this space. And in fact, it's categorification as well. So you can do not just cohomology invariants, you can do K-theory invariants or whatever you like. Okay, so let's see. That's all I wanted to say, I guess, about enumerative theories. Let's go to part 3. Any questions?
First, when you say they introduce a W-dependent virtual cycle, you mean?
Virtual fundamental cycle.
Yeah,
class.
that cycle is on the critical locus of W. That's what
So this is a cycle in this space, but it is supported on the maps that map to the critical locus of W. So it's like, if you have a very badly behaved space, and you want to kind of to integrate in it. So one way to do this is you're making slightly better behaved space, and then you're putting in a cycle which is bad, but you're still integrating this better space, so you can actually manage. Okay. Yeah, in fact, this is made by actually introducing a bigger space, but let's not worry about it today. So, part 3, invariants. So the way mathematicians produce invariants out of these theories is, again, take this space and then integrate something over the virtual fundamental class. So, and today I'll be only considering the invariants corresponding to these loop spaces. So when you basically take a P1, maybe orbifold P1, and then with mark point. And then you have the evaluation map at your marked point. So you have a curve, and then you have a point, and then you can just look at where this point lands. And this is going to be, well, not quite in XZ itself, but it's going to be in its inertia stack in the orbifold case. But again, if you don't worry about this, just think about this. And again, there are many ways to define invariants. But basically, let's see, to save some time, I can just not talk much about this. Okay, so one generating series of invariants, which is very important in this business, is called I function after Giventhal. And where I actually stands for integral, because these functions can be, their components are represented by oscillating integrals through the mirror symmetry, but that's some background. So this is going to be a function of a bunch of variables Q, which will correspond to a complexified Fourier-Dupuis parameter, or Kähler parameter, stability parameter for space X. So you can think about it as exponential of zeta plus I theta, where theta is the theta angle. And additional variable z, which is in the sphere or hemisphere language, which is going to be radius. Again, complexified radius of the hemisphere or sphere. Because in the sphere or hemisphere, you can put some actual metric, which is supersymmetry invariant, and then this metric will have a radius. Okay. So, and this I function is going to be basically a prefactor times a sum over degrees and then there's going to be the part of the classical action, which is just going to be q to the d over z. So this is a vector variable. And then what we're going to do, we're going to just integrate in the fibers of the evaluation map. Well, mathematically, it's a push forward. And then this is going to be some equivariant push forward. So it's going to be defined by some localization, but let's not worry too much about this. And what we're integrating is just the virtual fundamental class itself. So the simplest kind of generating series you can imagine. Okay. So, okay. And technically, this is going to be what? So this is going to be something that is valued in the cohomology of this. And the cohomology, so it's actually going to be some version of relative cohomology. So let me actually not, let me write the wrong statement, but it's going to be just simpler. So I take a relative cohomology relative to the locus where the real part of W is very, very large. So W over Z. Again, this is not quite true. And then this is going to be function in Q and in Z. So scalar variables or Fourier-Luppol's parameters and radius. Okay. And well, okay, so this is going to be a round polynomial with Z, and then this has some logarithmic dependence on Q, because logarithm of Q is actually Fourier-Luppol's parameter, and then it's going to be formal power series in Q, which is like instantons or vortices contribution. This will not always converge. So sometimes this will be like a formal power series as it happens, right? Here.
Yes, so these are the holomorphic sections of the equivalent bundle.
Yep.
And so you count them.
Right.
Okay.
Exactly, yeah. Huh? This one?
Yeah.
Well, which one? Z.
Yeah, this one.
Well, so otherwise things might just not converge. It somehow counts the, yeah, I don't want to say the wrong word in physical language, but it counts the homogeneity degree of the whole thing. In the Calabi-Yau case, for example, you can just set it to 1 and forget about this. But in physical language, yeah, I think this will correspond to radius of the sphere when you're doing like honest supersymmetric localization. Okay, so finally let me state some result. So what we showed with Melissa Leo last year is that, well, if you smartly count this, if you smartly make like an actual function out of this, you'll get the Fourier-Roma hemisphere partition function. So, and what we do is, so basically you take this I function, evaluate at minus Z, and then you multiply it by some explicit cohomology class. So this is called Iritani's gamma class. And then you multiply it by the modified Chern character of some matrix factorization of W on X. So this B is matrix factorization of W. So this is a pair of vector bundles with two maps, where the composition is just W times the identity, I guess. E1. Which are known to be related to the actual brains of the theory, like open string boundary conditions for such theory. Well, in this thing, we show that it is equal to, defined in this curve counting formalism, is equal to the Fourier-Roma hemisphere function, so which is going to be some Mellon-Barnes type integral over some explicit contour, which you can write. So this is going to be, this variable corresponds to scalars in the gauge multiplet of the GLSM. And then there is going to be a gamma class of just vector space E times just usual character of of the corresponding, well, this E0 and E1, those just representations of G, like vector spaces. So you can take the Chang character of, so there is some Z dependence as well, but it's. So B tilde is a matrix factorization on V such that if you restrict it to X, it's going to be B. Right, and then we have this thing. So this is Hori-Romo hemisphere function in the physical literature. Okay, and the way to think about this, so it looks like a Fourier transform, and in fact it is an inverse Fourier transform with respect to the variables Q and sigma of just the gamma class multiplied by the Chang character of B tilde.
Why the tilde? Sorry, I got distracted.
What is that?
Why you have the tilde there? B tilde?
Well, because technically B is a brane on X, and B tilde is a brane on V, just G equivalent brane on V. But this is just a restriction of, yeah. One, like this is an equivalent matrix factorization on V, and this is just non-equivalent matrix factorization on X. But some technicality. Okay, so technically we proved this in general case where group G is abelian. And so in the version archive, this is for Calabi-Yau case where G is a solid V, but this is actually true in non-Calabi-Yau case. Mm-hmm.
Is gamma cat with C, and here is gamma cat
with V and Z. Yeah. So let me put here X and Z. So gamma class is actually a cohomology class which is well defined for any equivariant manifold. And this is just an equivariant gamma class of X. This is just a equivariant gamma class of V. It was defined by Edith Tanya like almost 20 years ago. And then Z tells that you have to homogenize everything with respect to Z. It's like a well-known phenomenon in Frobenius manifolds. When you have to, maybe I can talk about this like a bit later in more details. But essentially, so this is product of some gamma functions. Of what? Of the scalar component of the gauge multiplet, sigma, and R charges. Okay? So this paper is now under heavy revision, but yeah, the result is there. Can I have a couple more minutes?
Yes.
We'll start a little later, but. So this is one of the results we have. So another result is, so in the upcoming paper, this is, it's been submitted to some proceedings, but I haven't put it on archive yet, is that, well, now if you take some weird sign change, so degree over 2 minus n over 2, where n is dimension of x, times the I function of qn minus z, and then you pair it with a complex conjugated I function, which is given in terms of gamma classes. So bear with me a little bit, but with I function itself. So this is a non-standard complex conjugation. Right. Exactly. So this is equal to the sphere function of being Cremonese, and then the Rode, Lefloch, Bruno, Lefloch, Lee. Hope I didn't forget anyone. Sphere partition function. Being Cremonese. The Rode, Lefloch. I forgot someone.
Gomes.
Oh, Gomes, of course, yeah. Gomes, Lefloch, and Lee. Right. So this is something very familiar in Trieste. Anyway, so yeah, this is only true in the Calabi-Yau case, as it should be, because right. So this is Z is actually 1. Sorry. In this case. Okay. And again, G is general abelian. So in the non-abelian case, we also have ideas how to show this, but it just requires a little bit more time.
Sorry, but this you did for genus 0, no?
Yes, exactly. This is all genus 0. This is all this loop space computation.
Of course, because. But then if you try to do it at higher genera, what do you get? Because then, I mean, in the genus sigma model, typically you have to integrate over the moduli space of Riemann surface.
Right.
So, I mean, this in genus 0 is a rigid model, and then this is the localization.
Right, yeah.
But at higher genera, what would be?
So in general, I have no idea, because I mean, in some cases, let's say geometric phases or LG phases, people have proved that this mathematical GLSM reproduces what we expect, so it reproduces Gromov-Witten theory of stable maps, and then quasi-map theory, and then FGRW theory, or like singularity A model. But in general case, it's not known, right? And Favre and Kim proved that under some out assumption, this is actually a full-fledged cohomological field theory. So all the formalism, the Dubrovin-Young formalism, given tal formalism can be applied to it. So if it's semi-simple, you can reconstruct, right? If it's not semi-simple, then I don't know. So there are several groups of mathematicians who are working on higher genus invariants, but they're still, I mean, and they succeeded in many examples. Let's say the quintic. I think they computed they reconstructed the all genus theory for the quintic threefold, like they reproved the homomorphic anomaly equations and things like that. But yeah, in general, it's very much open problem.
Did they really compute the invariants or reproduce?
Again, just reproduce, yeah.
I mean, the equations.
Yeah. I don't think they. I might be wrong. I hope they won't see this video, but in my impression, they didn't fix all the homomorphic anomaly. But again, I might be wrong. In principle, they have a model where it could be fixed, but I don't think they did. Right.
So who are these?
So there is this group that works on MSP fields. So there is a Ruan group. There is also, I think, Tian group works on this. So like there are this lot of mathematicians working on it. All right. So yeah, maybe a couple of more words about this. So we also have a K-theoretic generalization. Which should correspond to 3D gauge theories. So we should generalize some results of Jokers and Meyer. And then we introduce some analogous functions. So these functions, we call them quasi-central charges because, yeah, if those are convergent, then for fixed values of parameters, they should be related to central charges of D-branes, and they also should be related to central charges of some region stability conditions. But then we introduce some elliptic central charges, so we can compute K-theoretic invariants, and then insert some elliptic cohomology class to get interesting partition functions. Then there is wall crossing. So there are well-known conjectures about how these objects behave for different stability choices for GLSM, and then we have some results on that. And then we also constructed some interesting GLSMs that provide the open-close correspondence for some invariants. For real quintic. So Walcher, Pandaripande, Solomon reproduced, constructed some invariants, some disk invariants of the quintic threefold, so which just corresponds to like A model bulk twist with A model boundary conditions. And then we constructed some GLSM that whose closed invariants, or in other words, such that its central charge, one of its central charges is equal to the discounting for the real quintic. And this is also something people have not thought about. Okay, but yeah, I think I'm over time, so let me stop here.
Other questions?
About this I series
Mhm.
invariants. Does something happen if I count similar thing on the mirror problem?
On the what? On the mirror? Right, yeah. Actually, I forgot to mention that, yeah, I also have an upcoming paper about the mirror. So, yeah, people predicted of course, people know what the mirror of GLSM should look like, more than 20 years ago, like Hori and then many other people, right? Giventhal. So what you can do, you can compute the mirror integrals, right? And then there is a nice ways there is a nice homological mirror symmetry formalism that, so let's say you have a brain, right? You have matrix factorization. And then you want a mirror integral. And then you can actually represent, again, under some mild assumptions in the abelian case, you can represent like a mirror of a given matrix factorization by a particular Lagrangian in the mirror. And then you can make an oscillating integral over that. So you'll get some period. And then this is going to be equal to the central charge of right. So this is compatible with mirror symmetry, of course.
So all of this depends on the choice of stability, right?
Of course. So that's where wall crossing is, which I haven't mentioned yet.
So you can choose whatever stability you like, or you
No.
can stay outside some walls.
Exactly, yeah. So if you, of course, the only way, so this works on the nose is when all the stable points, semi-stable points are actually stable in technical terms, or in other words, when your vacuum space does not have only discrete gauge residual symmetry, or in other words, it's an orbifold. But yeah, there are actually some very nice, interesting works about how to make these things work for the non-discrete gauge symmetry. But I think they're in very there are some works by Dan Happy-Leisner and Fernando Herrera, but I think they're still very much in the development. But the point is, yeah, so the nice way how I like to think about this is that in each chamber you have this power series representation, but on the walls you have some integral representations. And then you could think, I mean, it's very heuristic, but you can think about such integrals. You can also partially integrate. So on the walls you can partially integrate in some directions, then you get some power series of integrals. And then you can think about, again, this is very heuristic, but you can think about this like power series whose coefficients are integrals as a wall partition function, right? When you have some non-trivial column range. And yeah, and when you go to some deep in some chamber, then it's going to reproduce you the actual thing.
And did you try to create a non-abelian GAT?
Yes, I think it should work. So it requires some more work on the mathematical formalism of quasi-maps. So I think in the case without superpotential, Rachel Webb has computations of like there is some abelian and non-abelian correspondence for I functions. So if you don't have a superpotential, then this theory is simpler. And then in this case, Rachel showed that for non-abelian case you can also define this type of I function, and this can be related to the I function with respect to the maximal torus of the non-abelian gauge group. Yeah, for example. And then except it doesn't, for now it doesn't work like with superpotential. But in this case, on the nose we can also use absolutely the same method we just say, because we have like the I function, and then we can just use the same methods to prove that it is true. So yeah, that would be the short answer.
not, we thank Konstantin again. Very good. Thank you.
Thank you.
And now let's